Welcome back to this course on organic chemistry in biology and drug design. Last time we have discussed the aspect of enzyme inhibition, and we have seen that there are different classes of enzyme inhibitors, but broadly speaking they can be classified into reversible and irreversible. Okay. And then in the reversible side we have different kinds depending on which active site the inhibitor is binding. Okay. So, accordingly there are competitive inhibition, there are non-competitive inhibition, there are uncompetitive inhibition, and and then mixed inhibition. Okay. So, before we go on to the next topic, better to clarify some of the doubts, I thought that it is better that we do some problems, so that the concepts become more clear. Okay. So, here we start with a first problem, that there is a enzyme kinetics graph that is given here, and this graph is obtained by plotting the V, actually this is the V 0, the initial velocity. It has a unit, that is micromole per minute, and then on the x axis you have substrate concentration, but that was multiplied by 10 to the power 3 in order to express it into the in molarity units. Okay. So, this is your graph, and now what is asked, that you calculate from the graph what is the value of Km. Km is the Michaelis-Menten constant, Vmax, that is the maximum velocity that is possible for this enzyme catalyzed reaction, provided you have enzyme concentration same or some specified value. Then K 2 by Km, that gives, I told you last time, K 2 is the second, that the rate constant for the breakage of ES complex into the enzyme and the substrate, and Km is the gives the dissociation constant of the enzyme substrate complex into the substrate, the starting substrate and the free enzyme. Okay. However, this K 2 by Km is an important parameter. I told you that this is this actually denotes the catalytic efficiency of the enzyme, and then the fourth one, that calculate the turnover number. Okay. So, let us go step by step. Now, we know that the first what is being told to calculate is Km. Now, Km can be defined in two ways. One, as I told you, it is the dissociation, it is a measure of the dissociation constant of the enzyme substrate complex into E plus substrate. It is also the concentration needed to reach half of Vmax. Now, here I give one more data that is missing here, that the enzyme initial, the concentration of the enzyme in this experiment is supposed 10 to the power minus 3 micromolar. Okay. That is needed to calculate some of these parameters. Now, we start with not with Km, we start with Vmax, because once we have Vmax, then we can draw the lines to see what is the concentration needed to reach half of the Vmax. Okay. So, let us draw a line here. So, Vmax is approximately according to the graph, it is little less than 6, but let us draw a line, and which will ultimately touch the maximum velocity line. Okay. So, we can say that 6 micromole per minute, this is your maximum velocity, that is equal to Vmax, okay, according to the graph, because that is the saturation level. What is saturation level? That means beyond that you cannot increase the rate of the enzyme reaction, that is not possible unless you add fresh amount of enzyme. Okay. So, in this the enzyme concentration is specified 10 to the power minus 3, and so the value of Vmax is 6. Now, how to calculate the value of Km? Km is basically the substrate concentration needed to reach half of Vmax. So, what is half of Vmax? So, this is the 3. So, half of Vmax is 3. So, this is the line denoting the half of Vmax. Okay. So, you just draw this line and then try to see what is the value of the x axis. The value of the x axis I see is 0.5. Now, that means this is 0.5, but remember one thing, this axis is represented by substrate concentration into 10 to the power 3. So, this 0.5 is equal to the actual substrate concentration into 10 to the power 3 moles molarity. Okay. So, S is now 0.5 into 10 to the power minus 3, okay, 0.5 into 10 to the power minus 3 moles. So, that is the value of S. You can write it into 5 into 10 to the power minus 4 molar. So, this is basically the concentration needed to reach half of the Vmax. So, here this value should be equal to Km. So, now we know what is Km and what is the Vmax. What is the third parameter? That is, you calculate K2 by Km. We already have the Km value, but we did not have the K2 value yet. Now, remember from the Michaelis-Menten equation, you know that Vmax is equated as K2. Remember, K2 is basically what? E plus S going to Es and then Es going to the product P plus E. So, that is the K2 that we are talking about, and this is usually written as K1 and this is K minus 1. So, we need this value K2. So, K2 is related to Vmax by this equation, that if you multiply K2 by the enzyme concentration, you get Vmax. So, now you have Vmax and you have E0 that is mentioned 10 to the power minus 3. So, K2 will be equals to, your Vmax is here 6 micromoles per minute, 6 micromoles at minute inverse divided by your enzyme concentration, and that is 10 to the power minus 3 micromoles. Better write these units, so that you know that you are using the same units for the concentration. So, here this is micromoles, so that crosses out. So, ultimately K2 becomes equal to 6 into 10 to the power 4 minute inverse. Okay. If you convert it into second inverse, then you will get 6 into 10 to the power 4 into minute inverse means 1 by 60. So, that will be second inverse, and if you calculate, that will come as 10 to the power 3. Let me see whether 6 into 10 to the power, sorry, we start with 6 into 10 to the power, there is something wrong here. The eraser, this is not 10 to the power, this is your 6 into 10 to the power minus 3. So, 6 into 10 to the power 3, okay. 6 into 10 to the power 3, and so that will be 10 to the power 3. Again, I have to erase that, just a second. This is your 10 to the power 3 into 1 by 60. So, that will come out to be 10 to the power 2, that means 100 second inverse. So, that is your K2. So, then K2 by Km, that is easy, you just divide K2 by Km. We have already got Km, that is in, but that is in molarity. So, what is your then K2 by by Km is equal to, basically K2 is 100 second inverse divided by 5 into 10 to the power minus 4, and that will be M inverse, and the unit will be M inverse, and K2 has a second inverse. So, that is second inverse, that will be the unit. So, you can calculate this and then find out what is the ultimate value. And the last one is, so we have done this, that one, that one, that one. So, the last one is turnover number. Now, what is turnover number? Turnover number, if you remember that I said turnover number was basically the value of K2. K2 has different names. K2 is sometimes called Kcat, catalytic constant, but it is also known as the turnover number. Now, turnover number is the number of substrate molecules which are turned over into the products by each single enzyme molecule per, it could be per time inverse, means it could be per second or per minute. So, whatever K2 you have here, that is equal to the turnover number, TON, turnover number. So, that will be again 100 second inverse. So, what does it mean? That means, in 1 second 100 molecules of the substrate are converted into the product by a single molecule of the enzyme. However, there is one assumption here, that the enzyme has only one active site for the substrate. Again, remember what I said, that turnover number is the number of substrate molecules turned over into the products per unit of time, in this case second. So, per second 100 molecules are converted into the product by one molecule of the enzyme, and but there is one assumption that is there, and that is the enzyme should have only one active site, because some enzymes may be in dimeric form and they can form two active sites. So, that is possible. So, those are excluded. It is only the general case where we consider that each enzyme has one active site for the substrate to bind and then convert it into the product. We go to a second problem. Okay. The second problem is, which of the following statements is correct? There are several statements given here. The turnover number for an enzyme chymotrypsin, we are now quite conversant with chymotrypsin, chymotrypsin that hydrolyzes peptide bonds specific to aromatic amino acids, and the turnover number is 100 second inverse, like the earlier problem, turnover number came to be 100 second inverse. And for another enzyme which is called DNA polymerase, we have not yet read the nucleic acids, but DNA polymerase is the one which actually synthesize the polymeric DNA molecules. Okay. So, DNA polymerase has 15 second inverse. So, turnover number here is more than this one, 15 second inverse. Now, what does it mean? Something having a higher turnover number, and we are comparing with an enzyme which is having lower turnover number. This means that chymotrypsin, now you have to find out the correct statement. Chymotrypsin binds its substrate with higher affinity than does the DNA polymerase, whether it is correct or not. Now, turnover number is basically the K2, that means how quickly the ES is converted into the product. Okay. It does not have any connection with the with your higher affinity of binding, substrate with higher affinity. Higher affinity, it does not have any connection, because affinity means the stability of the ES complex. Okay. If the ES complex, if the Km value, affinity is directly related to the Km value. If the Km value is low, that means the dissociation is low, the association will be more. So, in that case the binding affinity is more for the substrate. Okay. So, turnover number has nothing to do with binding with the affinity for the substrate. Chymotrypsin binds its substrate with higher affinity than does the DNA polymerase. In the equation also in K2, you have seen Vmax equal to K2 into your enzyme concentration. There is no mention of any Km. in that equation. So, first one is incorrect, you cannot say that. The second one, the velocity of the chymotrypsin reaction is always greater than that of DNA polymerase reaction, whether this is true or not. If you use the same enzyme concentration for chymotrypsin as well as for DNA polymerase, then this statement becomes true, but nothing is written about it. Says that it is always greater than that of DNA polymerase. That may not be true, because if you start with more DNA polymerase, more enzyme to start with, then what will happen? Then your then it can have a higher velocity. The DNA polymerase can have higher velocity, because if you have higher concentration of the enzyme. So, that is also not true. The velocity of the chymotrypsin reaction at a particular enzyme concentration and saturating substrate levels. Saturation means that Vmax value. When you have lot of substrate, that means all the active sites are blocked there. The velocity of chymotrypsin reaction at a particular enzyme concentration and saturating substrate levels is lower than that of DNA polymerase reaction under the same concentration conditions. No, it is not correct. Actually, you are now using the same enzyme concentration. So, obviously, chymotrypsin has a higher turnover number. So, that cannot be lower than that of DNA polymerase. Okay. So, obviously, the fourth one has to be correct, because all these are incorrect. And the velocities of reactions catalyzed by both enzymes at saturating substrate levels could be made equal if 6.7 times more DNA polymerase than chymotrypsin were used. Again repeat, the velocities of the reactions catalyzed by the enzymes at saturating substrate levels. That means, at saturating substrate levels, the velocity of the reaction is equal to the Vmax. At saturating means when you have saturated the active sites. So, Vmax the Vmax for chymotrypsin. Okay. So, chymotrypsin Vmax will be what? Turnover number of chymotrypsin is 100 into, suppose you are using the concentration of chymotrypsin, the concentration of the enzyme, this is Vmax. Vmax is related to K2 into enzyme concentration, total enzyme concentration, and suppose this is your chymotrypsin, and chymotrypsin, suppose that is, I call it that you are using X. X is the molarity of the enzyme, X amount of enzyme you are using. So, this is for Vmax for chymotrypsin, I am just abbreviating it, okay, chymotrypsin. So, that is the Vmax. So, for DNA polymerase what will happen? You are using enzyme concentration which is 6.7 times. DNA polymerase is 6.7 times concentrated than the chymotrypsin. So, in that case, Vmax will be equal to what? It has got a turnover number of 15, this means K2, and then the enzyme concentration of polymerase. So, that will be equal to 15 into how much in relation to x? You are using 6.7 x, and if you calculate, that will be approximately equal to 100 x. So, this is also 100 x and that is also 100 x. That means, the velocities of the reactions at saturating substrate levels could be made equal, they are made equal, provided you use 6.7 times more enzyme concentration in case of DNA polymerase as compared to the chymotrypsin. Okay. So, just on the basis of turnover number, you cannot just really say that always the reaction will be faster for the on the basis of turnover. One enzyme which has got higher turnover number does not mean that enzymatic reaction will always be faster as compared to others, because what you need is the, apart from turnover number, you need the enzyme concentration that you are using for the reactions to carry out. Okay. So, next go to the third problem. Okay. Third problem is basically an inhibition problem. Earlier it was just Michaelis-Menten equation we used, and we have determined the various parameters. And the second problem was quite interesting, because it also clears some doubt, because a lot of people have doubts that which factor really says that an enzyme efficiency is very high. I told you that enzyme efficiency is inversely proportional to what? Is inversely proportional to Km, because higher the Km, more will be the dissociation of ES complex. That means, less will be the concentration of the ES complex, and it is only the ES complex concentration from which the product is generated. Okay. So, Km, higher Km means lower ES concentration. So, velocity is inversely proportional to Km, and velocity is directly proportional to K2. K2, that is the turnover number, or K cat as also called. So, K cat more means more number of ES molecules will be turned over into the products in a smaller time. Okay. So, that means directly proportional to K cat or K2 or turnover number. So, ultimately the efficiency is given by, when you join these parameters, is the value of K cat by Km, that gives the enzyme efficiency. Okay. Now, this is another problem. Well, let us erase the. Now, here there are again, this is a this is not a Lineweaver-Burke plot. This is the normal. If you plot from the enzyme Michaelis-Menten equation V versus S, you will get a curve like this, that it goes up and finally it reaches the saturation level. Okay. And there are 4 curves that are given here. This is for the same enzymatic reaction, for the same enzymatic reaction. Okay. For the same enzymatic reaction, for the same enzyme concentration, all conditions are kept similar. Only there are 4 curves. In one of the experiment there was no inhibitor, and one of these curves represents that kinetics. Another one is where an inhibitor is added, which is non-competitive, okay. And you have to find out which curve actually fits to the non-competitive inhibition. Then the competitive inhibitor, then another experiment was done using a competitive inhibitor, and you have the corresponding the kinetic, the graph. And the fourth one is a mixed inhibitor. So, all these 4 conditions are given: no inhibitor, inhibitor first non-competitive, then another experiment competitive, and the third and the fourth one is mixed inhibitor. Okay. So, let us see in first of all, the out of these 4 curves, what you are seeing, that the velocity, initial velocity, see the velocity when the substrate concentration is low, this curve has the highest velocity at this curve, because this is the fastest growing. This has got the highest gradient. Okay. So, that means this has this curve represents highest value of the velocities. So, if that be the case, then this is the one where there is no inhibitor, because inhibitor slows down the reaction. So, if there is inhibitor, no inhibitor, then the normal enzyme kinetics, normal means the fastest growing curve, that will be your that will be followed when there is no inhibitor. So, 1 is basically where there is no inhibitor present. I hope this is clear. That is just from the gradient I can decide, because this is the highest value of the velocity, followed by this one, followed by this one, and this is the fourth one. So, you are slowly decreasing the value. That means, these are definitely the curves for the inhibition in presence of inhibitor. Okay. Now, we have to find out which type of inhibitor gives which curve. Okay. So, we have decided that the number 1 is does not have any inhibitor, no inhibitor. Okay. So, now let us see what is the Vmax. So, this is the Vmax without inhibitor, no inhibitor because this is number 1. This is the maximum velocity that you get under saturating conditions. Now, you look at the number 2 curve. Let us go one by one. Number 2 curve, what you see that this started slowly, but then as you increase the substrate concentration more and more, ultimately it reaches, these two are almost same. The Vmax value is almost same for 1 and 2. There is minor discrepancy, but you can neglect that. So, Vmax value for 2, what is seen that Vmax is same. Same means same as 1, where there is no inhibitor. Okay. Now, this is the number 1 curve which has no inhibitor. So, let us, what will be the Km value? So, the Km value will be somewhere, that is the half of Vmax, and you draw a line. So, your Km will be somewhere, this is the point, and you see what is the x axis. So, this is your, this gives your Km. Okay. So, if you consider the number 2 curve, the Vmax is same, but what about the Km? Km is again half Vmax is value the same, if Vmax are same, half Vmax are same. So, if you now you have to now extend this up to 2. So, this is the where the line is crossing, the half Vmax line is cutting this graph, and now you draw the, try to a perpendicular to see the value of Km. So, for 2, what happens? Vmax is same, but Km is more as compared to 1. Okay. So, now you see in which type of inhibitors Vmax remains the same, but Km is more. Remember, what is the competitive inhibition? That when both the substrate and the inhibitor goes for the same active site. Okay. And if you bump or if you make the substrate concentration very large as compared to the inhibitor, then ultimately inhibitor becomes insignificant. So, you reach almost the same Vmax like the earlier one, as if there is no inhibitor. But what changes there is not the value of Vmax, because you will reach the same Vmax using a higher concentration of S. So, to reach half of Vmax, you need now more concentration of S. So, more concentration of S means your Km increases. So, this is the one, the number 2 graph must be for the, so no inhibitor is 1 and competitive inhibitor is 2. Okay. Now, let us consider the third graph. In third graph, I could see Vmax has changed. The value of Vmax is this for the third graph. Okay. So, for 3, I can write here, for 3, Vmax has decreased. Okay. What about Km? We have to see the Km. So, if this is the Vmax, then half of Vmax is somewhere here, half of Vmax. Okay. So, this is the half of Vmax for the curve 3, remember, and then you draw the line again, and this is connecting here, crossing the number 3 here, and then you draw the same perpendicular as was drawn for the absence of any inhibitor. So, in this case what happens? For 3 Vmax has decreased, but Km remains the same. So, which type of inhibition has that? That means, where the binding of the inhibitor and the substrate are independent of each other. when they do not have any relation, substrate binds to its active pocket and the inhibitor goes and binds to the another pocket. So, there is no sequence of binding, that it may be substrate first followed by inhibitor, or it could be inhibitor first followed by substrate. That is what is called the non-competitive inhibitor. They are not competing at all. Okay. So, in that case what happens? Km remains the same, because the binding of the substrate is independent of the binding of the inhibitor, but your Vmax will decrease, because no reaction happens when there is both substrate and inhibitor, both are bound to the enzyme. So, your effective ES concentration is decreased. So, your value of Vmax will also decrease. So, in this case, this is a case of non-competitive. So, that means 3 is non-competitive, and if you draw the fourth one, you will see that here Vmax has changed as well as the Km. So, for 4 Vmax decreases and Km also has changed. We are not seeing whether it is actually change, means it is also decreased, because if you draw the Vmax here, so Vmax will be somewhere this where, and then half of Vmax will be somewhere here, and then you draw the line, it cuts 4 here, and then you draw the line. So, Km is increased. So, Km has changed, in this case it has increased, and Vmax also. So, both are changed, Vmax is changed, Km also changed, and that is what is the case of mixed inhibition, where both the so mixed inhibition is the one which is number 4, where both Km and Vmax has changed. Okay. So, these things if you do practice more and more, you will be more comfortable with all these parameters and how to calculate them. If you enter into any enzymology lab, then this mechanistic enzymology needs to know that whether an inhibitor is a competitive inhibitor or non-competitive or this mixed. But one other inhibition, reversible inhibition, is not shown here in the graph, that is what is called the uncompetitive, where I remind you where the binding of the inhibitor depends on the substrate binding. The substrate goes and binds, and then the inhibitor follows. The active site is created for the inhibitor, and inhibitor goes and binds. In that case, what happens? The Km is decreased in that case. So, it cannot be uncompetitive here. Okay. Uncompetitive, if you do the if you this then in uncompetitive inhibition, see actually this same problem has been given to draw the Lineweaver-Burke plot, that means the what is called the double reciprocal plot. You know, double reciprocal plot is something like this. Suppose this is the normal reaction, no inhibitor. So, this is the graph for 1. So, now for competitive inhibition, we know that for competitive inhibition Vmax remains the same. So, for competitive inhibition, the graph for which one is the competitive inhibition here? Number 2. So, the number 2 will be this. So, this is now transferring this graph into a Lineweaver-Burke plot. So, you see that here the Km changes, Vmax remains the same, that is the competitive. For 3 remember 3 was our non-competitive inhibition. In non-competitive inhibition, the what really changes, what does not change is Km in non-competitive. So, the graph will be something like this. This is, remember, this is reciprocal. So, that means if V decreases, then 1 by V increases. So, it has to be like this, it cannot be lower than the number the straight line 1, because these are reciprocals. So, that is this is 2, this is your 3, and the number 4 is difficult to, it is number 4 something where both are changing. So, something like this, that is your number 4. Okay. So, that I think concludes this problem session on enzyme kinetics. Okay. Thank you.